Hello everyone. Now we'll look into the concept of AC polarography and cyclic voltametry. So first we'll look into what is AC current kind of thing. Right. So what is alternating current? See, the difference between direct current and alternating current is direct current, the flow of current is unidirectional from one electrode to the another electrode. It's a unidirectional kind of thing. This kind of current we see in a battery kind of thing. So which is used in DC polarography. Now coming to alternating current, the flow of current is not always in a one direction. The direction or the flow of current keeps on fluctuating after a particular time interval. That is, one cycle of current flows and then it changes to another direction. The current flows there. So this AC current is having an high voltage which is used in appliances and all kind of thing. So this AC current is applied in polarography. When this AC current is applied, it is called as alternating current polarography. Now this AC current has got a sine wave function, right? It is a sine wave current, what we call it as. It has got a forward direction current is there, and then another a phase, different phase current is flowing here. So this is called as an alternating. So the phase is alternating every time. So that's why it is called as an alternating current here. And the wave nature, what it get is a sine wave. So the wave shape of an alternating current is a sine wave shape kind of thing, right? So normally direct current, the current doesn't changes. The magnitude doesn't changes every time. Here the magnitude change, the current magnitude keeps on changing, and what you have at a peak, you get the maximum current value there, right? This the potential there is also maximum in this case, but in a direct current it is always constant all the time. All right. So this AC current is used in AC polarography. Now in AC alternating current polarography, alternating current frequency domain technique is used, which involves the superimposition of an alternative current voltage on a linear ramp. That is, you have this potential versus time linear ramp, right? So where the potential is increased linearly, this is a direct current potential. Onto this, an alternating current potential is applied or superimposed, right? So the alternating voltage is applied in this DC voltage range, and the AC component or AC voltage has a frequency. The used frequency is around 50 to 100 hertz of AC frequency is used, and the amplitude, that is the AC voltage what you have, is around 10 to 20 millivolt voltage is used. So this is the AC component which is applied onto the linear potential scan there. So this AC current component has got two waves, which the one cycle will have two regions, right? One region is above the potential, normal potential, one is below the one, right? So this curve what you get here, right, positive wave function and the negative wave function, what you call this two combinedly corresponds to one cycle, right? So there are many cycles of potential. So what you have that includes this frequency, that how many frequencies, how many cycles of current is there in one per second time, that is called its frequency. Now the one cycle, the cycle of AC component at E half value, if we consider, that is being shown in here, right? So at the E half value above, if the AC potential goes above the E half value, there occurs a reduction reaction where oxidant species takes up the electron from the electrode and undergoes reduction. This is above the E half value. And when the current voltage, applied voltage, goes below the E half value, there occurs an oxidation reaction where the reduced species which is formed here undergoes an oxidation. It means it loses electron, it undergoes oxidation and the cycle continues till the potential is in E half region. Once the potential is below the E half region, there is no reaction occurring. That is, before the potential is reached, E half potential is reached, there is no reaction, and after the E half potential, if the current goes beyond that, there is no reaction occurring there. So at E half only, so the current component what is measured here, because the reaction occurs at this halfway potential only, the current is measured during this process only. So previous to that before the E half value, what you get is you don't see any current kind of, because reaction is not occurring at that particular position. Only at the E half you see current generated, and you get a peak like plot in potential versus the alternating current plot, right? So nothing happens below E half, or that is below the E half values, there is no reaction occurring there, right? So reduction, so you have a reduction process above the E half value if the potential is above the E half potential, and below the E half potential, from there it goes back to the below the E half value, there occurs a reduction, and if it goes back, the reduction also occurs again. So a reduction and oxidation process keeps on reversing in this particular cycle. So the important thing here is that the system that can be used here is only which can undergo a reversible reaction. Non-reversible reactions cannot be carried out using an AC polarography. Only reactions systems which have a reversible process can only be used in AC polarography. So what is the measure of AC component of current is done. The current fluctuates only in the vicinity of E half value, because of a positive or reduction current is produced there above the E half value, and negative or oxidation is produced below the E half value. So only at the vicinity of E half, near to the E half value, only the current is seen. A peak is generated only near the E half, because it's only the region that is the current fluctuates there, right? So early in experiment there is no current generated. Late in the experiment also, the potential above the E half value, the total current is relatively constant, and there is no AC component to it. So it also, the signal also flattens out. So only you get a peak at the E half value only. So the frequency of AC voltage component applied is typically around, as we already talked, it is around 50 to 100 hertz. Irreversible process cannot generate AC wave. Right? The magnitude of AC voltage which is applied, normally it is 10 millivolts. In some cases 20 millivolts potential is also, AC potential or AC voltage is also applied kind of thing. This is a plot what you get for AC current polarography, right? So at the region, so let's say if E half value is somewhere around here, right? So at this position you will get the plot where the peak of the current is obtained, that is the AC current is obtained here, and the peak height, this current is directly proportional to the concentration of the electroactive species there, right? So the AC current is plotted against the potential, right? AC potential, the peak potential is same as that of polarography. So the E potential, the EP value what you get here, it is equivalent to the E half value, and the height or the amount of current generated there is directly proportional to the concentration of the electroactive species. So this study is suitable for electron transfer study, electron transfer kinetics, or is also used to study how many electrons are involved in the particular process kind of thing. This is the current equation that is for the AC polarography, where the peak current is given as n square f square a omega half d to the power half c delta E, where omega half is the frequency, the square root of frequency that is taken for the AC component, and delta E is the amplitude of the AC voltage that has been applied. So here as we already told, peak height is proportional, that is IP, the peak height how much you get is proportional to the analyte concentration. So the advantage of AC polarography is that detection limit is slightly better than direct current polarography, but problem is that it also involves a capacitive current. The capacitive current is not eliminated totally in a AC polarographic system. So AC polarography produces peak which solves problem of small wave on a top of a big. So resolution is slightly better in this case than the DC polarography. Multiple components give multiple peaks. Means if you have 2-3 electroactive species present in that, it will give different peaks for every electroactive species, because E half at E half only one particular species, at its E half it will undergo reduction or oxidation, giving a current there, right? And another thing is it can also be applied on solid electrodes. This AC potential can also be applied there. The next type of voltammetry what we talk about is the cyclic voltametry. So this involves a linear scanning of potential of a stationary electrode using a triangular waveform, right? So we have talked about this square waveform and the sine wave waveform. That is how the potential is here. In this triangular waveform, you have the wave increasing and then decreasing, right? You get a isosceles triangle kind of thing, right? So this is called as a forward scan region, and this is called a reverse scan region. So the potential is changed every at a particular position. So this kind of wave of potential that is used is called as a triangular waveform. And the thing is, this in cyclic voltammetry, the solution is unstirred. There is no stirring of the solution is carried out. It's totally unstirred solution. And this is the most widely used technique for quantitative analysis of redox systems, because it provides information on thermodynamics of redox processes, the kinetics of heterogeneous electron transfer reactions, and also it helps in determining the kinetics of coupled reactions also. Now, in a cyclic voltammetry, a 3-electrode assembly is used, a 3-electrode system is used. The current resulting from an applied potential is measured during a potential sweep. So the triangular wave, what you call, that is called as a potential sweep. So that is, you have a potential starting from around, let's say in this particular figure, it shows from plus 0.8 volt. The potential is increased till around minus 0.15, and then again the potential is brought back to plus 0.8. So this is the forward potential that is applied, and this is the reverse potential that is applied. And this particular potential where the scan is reversed, this is called as a switch potential. And the voltagram what you get is called a cyclic voltagram, which is a plot of current versus potential again. But the potential what you hear is about a sweep potential, which is having a switch potential. So the kind of plot what you get will be similar to like this. Let's see. Right. So here you have, this is one cycle of the forward and reverse scan, the second cycle. So like this, you can do a multiple scanning, right? So you have a forward scan, you have a reverse scan, right? So the current here, what happens is in a forward scan, from positive potential, it is going to the negative potential. So let's say from at A, initially there's some water molecule or whatever is there, oxygen is there, that is undergoing reduction. Then at a particular nearing to the E half region, the electroactive species undergoes reduction, and that gives you the cathodic current, the IPC, that represents the cathodic current, and the peak potential there, it is a cathodic potential what you get. So this is the cathodic current, because the reaction occurring at the cathode, that is the reduction reaction is occurring, and the current is generated there. So, and then it till the potential is, so this is potential is applied when you get this near to the switch potential, and once the potential is means E half is crossed, the potential reduces because the electroactive species concentration is reducing, right? And at this point the switch potential is reached, right? At the switch potential the potential is reversed, right? So it goes to the reverse scan, and because still the potential is in negative region, there still occurs any reduction of the any electroactive species left out, and that generates some current. But after a particular time, when it reaches to the E half value, the reverse of reduction occurs. The reduced species that is obtained in the above reaction undergoes oxidation, means
re-reduction is occurs. So it undergoes reoxidation and the oxidized species is generated. So this generates a current, and this current is called as the what you call it as anodic current, and this the peak, the anodic potential that is being obtained here. And then once the complete oxidation occurs, the current again reduces and it goes to its previous state where the scan is completed. And now again here the potential is switched back and the forward scan is carried out again. So like that multiple times the scan can be completed, right? So this is an example for scan potential, a sweep potential applied for potassium ferricyanide to potassium ferrocyanide system. So here the potassium ferricyanide undergoes a reduction to form potassium ferrocyanide by taking up one electron. The sweep potential applied is between plus 0.8 volts to minus 0.2 volts kind of thing. So let's see how the cyclic voltagram is obtained. The cyclic voltagram, why it is called, is because the current to potential curve what you get, it is in a cyclic nature kind of thing. That's why it is called as a cyclic voltammetry. So let's see about the cyclic voltagram obtained by for ferrocyanide couple. Right. So this is the cyclic voltagram obtained for the potassium ferricyanide in 1m potassium nitrate solution. So initially what you see is at A, let's say it is the start of the reaction, there is no current generated, initial range, the negative current due to oxidation of water to oxygen it gives. And then there is no reaction, no current between plus 0.7 to plus 0.4 volts because no reduction occurs, or oxidized species present in this potential is it doesn't undergo any reduction because it has not reached its EF value. So at B, what happens is at 0.4 volts current begins to increase because of the reduction reaction, that is ferricyanide converts into ferrocyanide, Fe plus 3 converts into Fe minus Fe plus 2 by taking up one electron. So this is the reduction reaction occurring, and there occurs a increment of current, and this current is called as the cathodic current, right, IPC, and it rapidly increases from B to D. The current is increasing as the surface concentration of the ferricyanide decreases because it is getting reduced, converting into ferrocyanide. So the ferricyanide has to move from the bulk of the solution to the electrode surface, so diffusion increases, so the diffusion current also increases. So anodic current what you get is also more in that case. So at this case rapid increment of current is seen. At D, the cathodic peak potential, that is the cathodic peak is very high, and that peak current is called as anodic current, cathodic current, that is IPC kind of thing. And from D to F, then again the diffusion, because maximum amount of electrolyte species is moved onto the electrode surface, it is reduced. The concentration of electrolyte species in the near to the surface is decreased, and the diffusion layer increases. So means it extends to the bulk of solution. So the diffusion current also slightly reduces from E to F kind of thing. So at F, there is point F, there is no reduction further happening, so the potential is switched. So the switch potential here is around minus 0.15 volts. So potential here is still negative. So if any traces of your ferricyanide is left out, it undergoes reduction to convert into ferrocyanide. So you see a slight current there, but it changes immediately, and from F to J you can see here when it reaches near to the EF value, the reverse of the reaction starts. Whatever the ferrocyanide that is generated in the above reaction undergoes oxidation again. So the ferrocyanide converts into ferricyanide and it generates an anodic current. So from H to J, the current increases there, and this current is the anodic current, it is given as IPA, that is peak current, and EPA is the anodic potential, right? Anodic peak potential, EPA is given there. And beyond this point, the current again reduces, because all the accumulated ferrocyanide has converted to ferricyanide and it is used up, so the current reduces, there is no reaction, so it goes back to its normal state as the initial state at initial potential, how much it was there. And this scan can be continued for longer time, for many times, as every cycle will give you the same kind of cyclic voltogram kind of thing. Right, so what we get the information from this cyclic voltogram. So the important information what we get is the anodic current and the cathodic current what is obtained is equal for a reversible reaction. If the reaction is not exactly reversible, the anodic current and the cathodic current will not be equal. But if it is a reversible reaction, then the anodic current, the peak height of the anodic current and the peak height of the cathodic current will be equal. That is, if you see the height of this and this will be equal. So that is the anodic current and cathodic current. So difference between the peak potentials, that is anodic peak potential and the cathodic peak potential, that is delta EP, what we get can be equal to 0.0592 by n, right? So this helps. So if we can obtain the delta EP value, then we can determine the number of electrons which is transferred in a particular redox reaction. So this cyclic voltammetry is also helpful in determining the number of electrons involved in the redox couple there, right? So because here the n represents the number of electrons involved in the transfer of electron in the redox reactions. E naught is the midpoint of EPA and to EPs, right? That gives you the E naught values, and the peak current, the I value here represents is 2.68 in 10 power of 5 n to the power of 3 by 2 A C and to the power half and mu 1 2, where A is the electrode area, the same as the fixed diffusion constant for diffusion current what we have taken. D is the diffusion constant. The two terms what you have known is n, that represents the number of electrons, and mu which represents the scan rate, right? And C represents the concentration. Here again the concentration is directly proportional to the current which is obtained at the two cathodic current as well as the anodic current. So the current is directly proportional to the concentration. So what we can get is we can calculate the standard potential for half reactions, number of electrons in the half reactions, diffusion coefficients can also be calculated, and that is basically for a reversible reaction process. So the many applications are there for that, so that we'll see. But the reversible system, we say that the current peak is proportional to the concentration of electroactive species. It is proportional to the frequency, square root of frequency of the scan that is carried out. The ratio of peak current, that is the anionic current and the anodic current, the cathodic current is equal to 1 for a simple reversible couple. For redox couple, E naught is given as EPA plus EPAC, that is anodic potential plus cathodic potential, half of it. That's why I say E naught is the midpoint of anodic potential and the cathodic potential. The separation between peak potentials, the delta PV, is given as the 0.059 by n. So where n represents the number of electrons. Okay, so it is used to determine the number of electrons transferred in the redox couple. As I said, it has got many applications. It is applied in pharmaceutical industries for analysis of drug. It is used in analysis of herbicides, insecticides, foodstuffs, pollutants, pharmacological samples, and many kind of thing. One of the example we'll see that is a well-known insecticide which is used in agriculture sector. So this is a cyclic voltogram for agriculture insecticide paranthionine, whose structure is given here. It is having a nitro group, an ester linkage here, ether linkage here, right? So this is paranthionine, which is a insecticide, right, which kills insects, which is used as an agricultural insecticide kind of thing, right? So the switching potentials is between the minus 0.12 volts and plus 0.3 volt here. So there are different switching potentials being applied here, right? Because it is not exactly the reverse couple here, there's slight deviation from the normal expected thing. That's why you have got a different switch potential at minus 1.2 volts and at as well as at plus 0.3 volts. So initial forward scan starts at 0. At 0 volts the scan starts here, right? And you get the first cathodic peak at A. Now this cathodic peak this particular reaction is having, where the nitro group is reduced to a hydroxylamine derivative kind of thing, right? It takes up 4 electrons and 4 hydrogens from system to convert into an hydroxylamine derivative, right? So this occurs at this particular region, right, where the peak height is the cathodic peak. Then the current when the potential is decreases and you get a potential switch at this particular region, that is minus 1.2 volts. Here the cathodic current is reducing here. Reduction has completed. From here the potential is switched, and there you see at here what you see is a second peak what you get at B. So initially at particular time there is a still negative potential is there, so reduction occurs. After that there is no reduction, no switch is available for reduction. Then the E half value and the reoxidation of the oxidation of this hydroxylamine occurs. So what is expected is that on oxidation it should give back the nitro compound, but that is not seen here. What is seen is that at B this particular reaction is happening. The hydroxyl amine derivative is getting reduced into a nitroso derivative, which gives 2 hydrogens and 2 electrons is released. So it's not a complete oxidation process occurring here. So this on further switching the potential at around 0.3 volts, right? There occurs another peak here at C, where the third cathodic peak is seen. So this is again the third cathodic peak, where the nitroso compound which is formed undergoes reduction again. It takes up the 2 electrons and it converts into hydroxylamine derivative again. So at C you see this particular region, right? And then it comes to this particular. So the cycle goes in this way, where you see a different intermediate in this process. So this is how the cyclic voltammetry is helpful in determining the reaction intermediates also for a particular redox couple kind of thing.